The original SRO-1 system was developed in the Soviet Union as a form of identification for aircraft, naval ships, and various ground vehicles to increase better battle awareness of who is a friendly member to the Soviet Union or its allies. This initiative was most likely made due to the fact that jets kept getting better and faster, making visual identification of these aircraft difficult for the average pilot, and with ground crews who operated the new hot technologies of the time, those being surface-to-air missile systems and ground-based radar stations known as GCI, needed to have a way to identify a target as being a friendly or an enemy to the state from visual to beyond visual range to increase battle awareness and the capability of taking down non-aligned targets. Later, sometime during the mid to late 1960s, the system Silicon-2 was produced, which is SRO-2's and SRZO-2's combined system name, which is a modernized upgrade of the SRO-1 unit being able to perform its original capabilities better with increased range and data transmission times. Later in the early to mid-1970s, the Silicon-2M, that being SRO-2M and SRZO-2M, system would be produced to have better capability to resist jamming and to ensure secrecy of the IFF codes. The Silicon-2 system would be developed by NII-17 or NII-17 Falal, also known as OKB-15, which is a branch within Soviet aircraft development that focused on the manufacturing of radar systems such as radar units, notable examples being the early small portable radars RP-2 and RP-5 designed for the MiG-17P and MiG-19P PVO interceptor variants, weapon systems such as the RO-3 air-to-air missile developed for use with the MiG-19P and MiG-21F-13, IFF systems, and aircraft instruments. NII-17 was first established in 1944 by the USSR Council of Ministers for the Ministry of Aircraft Industry to streamline production of avionics-related equipment and named as TSKB-17, located in Moscow. On October 7, 1946, TSKB-17 would be redesignated as NII-17 because the branch would be reorganized to have separate sub-branches, those being NII-17 Falal and NII-17 Falal OKB-15, for different aspects of radar, weapons, and later satellite production. In 1967, NII-17 would then be redesignated as MNIIP, or today known as NIIP, which was turned into a private company at the end of the Soviet Union and has since then now been called the Moscow Scientific Research Institute for Instrumentation, or MNIIP, and still manufactures Russian Federation Air Force radars for the MiG-31, A-50 AWACS, missiles, and other military technologies. The SRO-1 would see the end of its service life very early in the Soviet Air Force, but the system would be installed in many export-only aircraft the Soviet Union produced for other nations, until these nations were certified for IFF upgrades, removing the old system and being replaced with the SRO-2 and SRZO-2. The SRO-1 would not see much, if any, service once the SRO-2 had gone into full military service and been outfitted to the Soviet Air Force and subsequent Allied nations. The Soviet Union would continue to predominantly use the Silicon-2 system until it began being phased out of service in 1972 by the modernization upgrade designated as Silicon-2M. Later, sometime near 1981, the PAROL system would be put into service, also known as SRO-1P. This was not supposed to happen so soon after Silicon-2M's development, but most likely after Belenko's MiG-25P landing in Japan incident may have pushed the Soviets to continue and finalize PAROL ahead of schedule. Then, after the SRO-1P system came the SRO-2P IFF system, also known as the PAROL 2. Other nations aligned with the Soviet Union would eventually get these IFF upgrades, but would often be downgraded for expert use to ensure the Soviet standard was always better than their peer nations. IFF systems in Soviet aircraft after the development of more advanced versions of IFF systems would see constant upgrades towards them to ensure protection of the aircraft from potential enemies knowing the specific codes for identification. Specifically, sometime during the mid to late 1960s, the United States military was successful in finding out how to break the IFF codes and sequences, and was able to find ways to track these aircraft based on their IFF signals. This would inspire the development of the SRO-2M, also known as Silicon-2M, system in 1972, which gained the addition for the codes to be more adequately encrypted. There are multiple times in history where foreign intelligence agencies were able to get their hands on and dissect these IFF systems. Those points in history being the defection of MiG and Sukhoi pilots in the early 60s to mid-70s is what brought the system's downsides to light naturally. A defection that sealed the SRO-2's fate alongside the SRO-1 was documented fairly well through the CIA's Freedom of Information Act, or FOIA, database. Within the FOIA, on the CIA's website, you can find a report evaluating the differences of the SRO-1 and the SRO-2, IFF systems. Now, this is the only instance I can find, but it would have provided the most new information gained for the American military. The only publicized instance that is not fully classified or widely known is a report done by the CIA detailing the occurrence of when a MiG-17F landed at the Hochstadt area in Germany on the 26th of May, 1967. After the landing of the aircraft, American military intelligence agencies had a limited amount of time to disassemble the aircraft and inspect the SRO-2 system within it. Although due to the time constraints in the report being labeled as superficial, as not enough time was allocated to study the devices. It would still give plenty of information, though, for the team responsible for disassembling it and give them the ability to compare it to data they already have for the SRO-1, confirming suspicions and learning how it would allow engineers to plan on how to exploit it once a full SRO-2 system was able to enter the U.S. The information gained from this defector's plane was invaluable for the time, as it allowed the comparison between the two IFF systems, and the agency responsible for the discoveries was able to note the differences. Then, later on, finding out how the SRO-2 system codes work and comparing them to the codes of the SRO-1, which were only in 5-digit range of Morse code, it was also found out that the SRO-2 system took up less space than the SRO-1 system, but had more cables connecting all the units together, which in turn made it take the same amount of space. From the data given, engineers within the U.S. Air Force would be able to make machines such as the QRC-24A and APX-80/81 that would use the SRO-2 and SOD-57 units to give detailed information of the aircraft. The data of the SOD-57 unit would give more specifically would be about the aircraft's height, speed, and fuel. With the knowledge of how the codes and frequencies work within the SRO-1 and SRO-2 systems, the U.S. Air Force would also make other machines that were capable of spoofing the IFF systems, making them useless in certain gone-hot scenarios, which led the Soviet Air Force to issue a developmental upgrade for the SRO-2 system, as well as the SOD-57 system, with the included automatic ability to have the codes and frequencies encrypted. This would be labeled as the Silicon-2M system, as well as the SOD-57M, and would lead to future generations of SRO to have better encryption systems. Though there's still one more defection that would bring the Silicon-2 system out of paradise and back into trouble. In 1974, Belenko, who was flying a MiG-25P, defected from the Soviet Union and landed at the Hakodate airport in Japan. The U.S. as well as Japanese intelligence agencies were able to take the plane apart and assess its equipment and capabilities. It was a reasonable assumption that the Soviet Union would likely see this moment as a compromise to the Silicon-2M system, as most, if not all, MiG-25Ps the PVO used were equipped with the Silicon-2M system. This would push for the creation of the PAROL IFF system, then at the time still being developed, to increase its research and development time and see operational use sometime near 1981 for the MiG-29. A prominent example of the advantage of breaking the SRO-2 or SRZO-2 and SOD-57 systems was when the U.S. Air Force exploited it with the creation of the APX-80/81 combat trait. With it, F-4D and later F-4E planes operating the APX-80/81 during the Vietnam War were able to identify Vietnamese planes based on the SOD-57 system alone by finding and interrogating the SRZO-2 system and SRO-2 system. Even if the MiG pilot was at treetop level, which would normally mask them from standard radar due to ground clutter, with this new ability added into the air battles of Vietnam, it greatly increased the F-4 Phantom kill count and aided the F-4 series of jets' renowned kill count. The AN APX-82 was a follow-up on the APX-80/81 and was installed in F-14s for the United States Navy. They were also exported. Although it was not as good as the AN APX-82, they were given to the Iranian Air Force for their F-14s, but the Iranian Air Force did not find much use from them due to the fact Iraqi pilots often turn off their IFF systems when going across the border into Iran during the Iran-Iraq War from 1980 to 1988. The difference between the SRO-2 and SRZO-2 in the Silicon-2 system is that the SRO-2 had no ability to interrogate air targets. It was only able to give the IFF request codes, which is why aircraft such as frontline fighters and ground-based radar stations, of course, saw the deployment with the SRZO-2 system, which had the ability to interrogate, whereas helicopters and transport aircraft saw the deployment with the SRO-2. The Silicon-2 system had 12 IFF codes it could use, those being 1, 1.67 MHz, 2, 2.33 MHz, 3, 3 MHz, 4, 3.67 MHz, 5, 4.33 MHz, 6, 5 MHz, 7, 5.67 MHz, 8, 6.33 MHz, 9, 7 MHz, 10, 7.67 MHz, 11, 8.33 MHz, and 12, 9 MHz. Code stations 1 through 3 most likely would have been used for aircraft operating the SRO-1 system. Code Station 4 wouldn't be used for testing and evaluating prototype aircraft and possibly foreign aircraft. Code Stations 5 through 8 were for standard everyday use, but the Stations 5 and 6 were used most often. Code Stations 9 through 12 were for wartime use only. The Silicon-2 system had an emergency distress option for cases of emergency while operating the aircraft, alongside a self-destruct button as well. This would indicate to other pilots, often through their radar display screens, that the pilot was in a bad situation and can tell authorities that the plane is experiencing difficulties. Since the SRO-1, Soviet IFF systems, even modern-day systems, have a self-destruct option to ensure secrecy of their IFF system. Somewhere in the cockpit would be a button the pilot could press in order to detonate an explosive cartridge within the Silicon-2 system itself and destroy all functionality of the system. To help in this fact, if a Soviet plane were to crash, the IFF system had the ability of, when 14.5 Gs were detected, would turn on a pressure switch, which would explode the IFF system on board the aircraft in case the pilot had forgotten to do it before ejecting in an extreme situation. For helicopters, though, the max G tolerance would be as low as 10 Gs. It is also very important to note that the SRO-2 can be paired with any IFF interrogator unit, such as the case of MiG-25Ps using the Violet interrogator. Not that long after the creation of the Silicon-2 system, the system itself could be used alongside the aircraft's main radar for easier interrogations and identifications of aircraft, as it would allow friend or foe symbols to appear on the aircraft's radar display screen. When paired with a radar for detecting aerial targets, the Silicon-2 system will send out a pulse signal at the 3 radar waveband while simultaneously sending a probing signal at the 1 radar waveband, while the radar station sends its own signal to get to the target. Since the invention of the PSBNM radar fitted on Il-28 aircraft had this feature and was also adapted for all known Soviet radars, such as the RP-21M or MA. This ability would be carried through all Soviet aircraft radars from here on. For the Silicon-2 system to be installed within an aircraft, there must be enough locations present on the aircraft that can accommodate 3, 2, and 1 radar waveband antennas, while at the same time causing as little overlap as possible. Specifically, each varying band antenna has a limit to where it can receive the Silicon-2's radar signals, thus requiring, depending on the size of the aircraft, as many strategically placed antennas have to be installed to ensure the system can work at a 360-degree circle around the aircraft in the vertical plane and the horizontal plane from any direction for friendly forces. For the larger aircraft in the Soviet Union's arsenal like the Tu-95 or other large aircraft, it can become quite difficult to equip them with the Silicon-2 antennas because more than the normal amount have to be present for such a large aircraft, while also maintaining the fact that the antennas don't accidentally interfere with each other while operating due to overlap, which is why there's a small limit for overlap and only allowed in less crucial areas of the plane. For installing the 3-band antennas on an aircraft's fuselage as recommended in Soviet manuals for best results, it is best to install 2 3-band antennas on the fuselage, 1.5 to 3 meters above or below from the front of the aircraft nose/inlet, and another set 1.5 to 3 meters above or below from the tail/exhaust nozzle to ensure that other SRO-2 and SRZO-2 systems can read and interrogate these aircraft from the front and back. Alongside 3-band antennas, there are also 1-band antennas. These antennas often get placed on the edges of wings. For the installation of the 1-band antennas, one should be at least 45 degrees and the other should be 135 degrees to coincide with each wing. Alongside that, the fairings for the 1-band antennas will often be shaped into the form of the wing to provide better airflow characteristics for the plane and conceal the antennas better, whereas 2nd-band antennas are primarily only used for communicating to ground-based radars from vehicles, radar stations, or ships. The SRO-2 and SRZO-2 system itself would be placed accordingly within the aircraft wherever convenient so that it didn't upset the flight dynamics of the plane. This was a fairly standard process and was usually somewhere along the middle of the fuselage, typically behind the cockpit of the aircraft. The entire SRO-2 and SRZO-2 IFF system consists of the following units, or known as blocks: decoder, Block 4, control box, Block 12-4M, transceiver, Block 5-OHM, T-divider, Block 13-4BA, T-box, Block 16-1, interface block, Block 6BM, control panel, Block 16A, restrictions and delay block, Block 16-2, 3-band antennas, Block 13-1AB, 1-band antennas, 2-band antennas, antenna boxes, Block 23P and Block 23L, junction box, Block 19, distribution box, Block 10B, explosion box, Block 1921, and the inertial circuit breaker, Block AR37. All of the items listed are both used by SRO-2 and SRZO-2, but Block 6BM and Block 4 are only used by SRZO-2. The decoders, or rather known as Block 4 within the SRO-2 and SRZO-2 index, main purpose is to average the signals coming into the unit by the receiver, which is modulated by the amplitude of the code's frequency by the receiver. The decoder is designed to limit the amplitude signals it receives as well. The last main effect the decoder does is the determination of corresponding frequencies received by the signal modulation to the set code and assurance that the frequency of the received signal corresponds to the established code, which is done through a pulse of constant amplitude and duration. A paralysis time no more than 5 microseconds, a delay of a signal within the decoder must be no more than 3 seconds, an output pulse no less than 25 volts, and an output pulse duration of no more than 3 plus or minus 0.5 seconds. The control box, known as Block 12-4M within the index, main purpose is to be switched on by the transceiver and antennas boxes, and is intended for testing of diodes within band 1 and 2 band antennas to supply voltage to the diodes within 1 and 2 band antennas, turn off the heterodyne, which is a combination of 2 frequencies to make a lower frequency within the receiver for the 2-band range to check the gain. The transceivers, Block 5-OHM within the index, main purpose is to receive SRO-2 and SRZO-2 requests for interrogations and responses for said interrogations by amplifying the request and response signals received by 3-band antennas, amplifying pulse signals from the radio stations detected by the 1 and 2-band antennas, and the output of the transmitter trigger pulse via the response channel if the received signal has an acceptable value and is a request signal used by the Silicon 2 system. The T-dividers, Block 13-4BA, main purpose is to connect the antenna cables to each other and connect the cables to the transceiver. The T-box, Block 16-1, main purpose is to provide a supply of video echo pulses from the tail protection station to Block 6AM or Block 6BM. Block 16-1B, on the other hand, is intended to send video pulses of echo from the radar PSBNM to Block 6BM. This is done so the SRZO-2 unit can give an identification mark for the PSBNM radar display screen. The interface blocks, Block 6BM, main purpose is to allow both the tail protection system and a panoramic radar with the SRZO-2 station to work together. The 6BM and 6AM will convert the output pulse of the decoder into a pulse that can then provide an identification mark, in this case a friendly or hostile symbol, on the radar display screen, though the 6BM and 6AM could only be used through Block 9 controllers. The control panel's Block 16A main purpose is to provide the main operator of the tail protection system the ability to control the SRZO-2 system. The restrictions and delay block, Block 16-2, main purpose is to clear the synchro signal of the air defense radar from parasitic impulses with the use of the 6BM and 6AM. The antenna systems a part of the SRO-2 and SRZO-2 system are the 3-band antennas, Block 13-1AB, 1-band antennas, 2-band antennas, antenna boxes, Block 23P and Block 23L, and junction box, Block 19. The antenna's main purpose is to receive the radar signals detected from the SRO-2 and SRZO-2 station. The 3-band antennas, Block 13-1AB and Block 13-3A, can either have a single prong, Block 13-1AB, or 3 prongs, Block 13-3A. Smaller planes, such as the MiG-15 or MiG-17, have to be equipped with the Block 13-1AB, because if the Block 13-3A antenna was equipped, it would provide too much overlap within the operational zone of the SRO-2 and SRZO-2 system. Whereas, on larger planes, if a Block 13-1AB antenna was equipped, it wouldn't be able to cover enough space as the aircraft's main body and tail would block it, which is when Block 13-3As would be installed. The main purpose of the 3-band antennas is to send response and request signals to the SRO-2 and SRZO-2 system within the 3-band radar wave. These types of antennas will usually be installed 1.5 to 3 meters at the front and rear ends of the plane's fuselage. The 2-band antennas, Block 12-12, main purpose is to receive signals from ground-based equipment such as early warning radars, ships, or GCI, and be able to communicate with those assets. These types of antennas will usually be installed on the lower surface of the wingtips. The 1-band antennas, Block 12-10, main purpose is to receive signals from any aircraft and ground-based radar with any polarization. An aircraft will typically be equipped with 4 of the Block 12-10 antennas, 2 on each wing, with 1 antenna at the front of the wing and 1 antenna at the back of the wing. The antenna boxes, Block 23P and Block 23L, main purpose is to connect the 1 and 2-band antennas with the transceiver unit and transmit video pulses from the antennas to the main video amplifier within the transceiver unit. In order to wire up all of the 1 and 2-band antennas, 2 or 3 antenna boxes are often used. The junction box, Block 19, main purpose is to connect the antennas to the antenna box, Block 23P and Block 23L. The distribution box, Block 10B's, main purpose is to supply voltages from 115 volts, 400 Hz, and 27 volts of power supply to all units within the system. The explosion button, Block 1921, main purpose is to electrically set off the explosion cartridge present within the SRO-2 and SRZO-2 system to ensure secrecy. There are 2 forms of the explosion button, Block AP1921 and the GB3604002, also known as Block 1921. The Block AP1921 only includes the button that will trigger the explosive cartridge and a light that shows the operational status of the SRO-2 and SRZO-2 system. If the light is on, then the system is still functional. On the GB3604002, Block 1921, there is a button present, a light, and 2 new additions. These are an extra distress switch normally seen on the Block 8 and Block 9 controllers, and a pin that requires the user to pull out to detonate the cartridge within the SRO-2 and SRZO-2 system in case the aircraft is on the ground and has no electrical systems online for an attack on a airbase. The inertial circuit breaker, Block 3-7, main purpose is to automatically connect the explosion circuit for the explosive cartridge in the event of an airplane or helicopter crash. This effect can be adjusted to 10 Gs or 14.5 Gs for the type of aircraft it is installed on. Later Soviet frontline aircraft saw the use of the Block AB or ABK. which was a simplified controller for the SRZO-2 code selection with the use of only the rotary switch present on the panel body. If these were present within the aircraft itself would have separate switches and lights inside the cockpit panels, typically near the 8B and 8BK, and to the right of the pilot that controls the SRZO-2 system. There will often be 3 accompanying lights. Some aircraft variants change this rule, but for the MiG-25P at the very least for demonstration purposes, these lights will designate to the pilot when code stations are active, a request signal is requested, interrogating, and when a request signal is being given, interrogated. When changing from one IFF code to another, the code station active light will go off and then back on after a second to show the changing of code station change. Although the positioning of the block 8B or 8BK and the accompanying switches with the lights can change in amount and position depending on aircraft variant and IFF interrogator. As discussed for the block 8Bs and 8BKs, the operation is nearly the same but is all done through the block 8A panel rather than using other panels within the cockpit, and was a more standardized format with no variety compared to using the block 8Bs and 8BKs. The Silicon 2M system uses many of the components from the SRO-2 and the SRZO-2, but adds 3 new blocks to ensure encryption of the IFF codes, known as product SKBO. These blocks being Block 30, Block 36, and Block 34. The SRO-2 8A controller block is the main control unit of the SRO-2 system, which allows the changing of code stations, the option of turning on the distress code, showing the pilot when the system is active, showing the pilot when the code stations are active, and showing the pilot when the aircraft is being interrogated. To start the SRO-2 system within the aircraft on the Block 8A device, and later Block 8s, the 2 switches combined by a small piece of aluminum must be put onto the on position, which is the up position, to start the SRO-2 system. Later Block 8s use a single switch though. The SRO-2 system has 12 codes to be used. These codes are changed to the code selector rotary switch in the middle of the device. Most rotary switches on the Block 8A is of the earlier version of the turnable rotary switch. On later Block 8s, this changes to a more circular design with insertions cut into it for better gripping. For storage or inactive use, a cover was supplemented with the Block 8s to protect the rotary switch handle as well. Beneath the code selector rotary switch is the protector case for the dial underneath with the codes labeled 1 through 12 that spins, and can be seen through a single glass hole at the top of it, all of which can glow in the dark. To the left of the code selector rotary switch is the distress switch. On top of the green metal cover has a label of disaster. In order to activate the distress switch, the green metal cover, controlled by a spring, must be moved upward, and then the switch underneath can be moved into the up position, also known as the on position. The switch itself has a glow-in-the-dark paint within it as well for nighttime operations. The top left light with the extended height house has a glass piece within it to protect the light bulb underneath it. This metal extrusion screws into the main device body. This light, when it turns on, communicates to the pilot when the aircraft is being interrogated by another. Labeled above it is indicator radiation. This light will turn on to inform the operator when the SRO-2 system is transmitting an interrogation request. The top right amber lamp indicates to the pilot when the code system is functional as being labeled code is on for the SRO-2 system. Next to the amber light is a green light that means power control. This light will turn on in about 1 to 3.5 minutes after the SRO-2 system is turned on to symbolize to the pilot that the system is fully operational after this time limit has passed. The Bakelite pill-shaped piece with female gold contacts is for plugging in devices to ensure operability of the SRO-2 or SRZO-2 system. Molded into the Bakelite is control. This is used by a device that tests the operability of the system. This can be done as a physical checkup of the system or being removed from long-term storage, which is 2 to 3 years. Above the three fuses is a white metal extrusion that is used to regulate electrical current through the system. Labeled above it is Reg EG. The three black fuses connected together by a wire allow function to the system when they reach the required voltage in amps to ensure the system isn't overloaded all at once. It doesn't hang while it turns on. At the bottom of the Block 8 controller, this also includes later Block 8s and 9s, are the connector cables. Only on the Block 8 and 8A controllers had 3 separate cables. Every other Block 8 and 9 had 2 cables, excluding the single rotary switch 8B, 8BK, 9B, and 9BK. But the cable with the female plug that consists of 4 connector pin plugs into the explosive button Block 1921, allowing the button to not only be connected with the SRO-2 system, but also detonate the explosive cartridge present within the SRO-2 unit when the button is pushed. This also allows the use of the distress switch from the Block 1921 to also be used in tandem with the distress function. Generally speaking, most Block 8 controllers were made with what was available at the time or saw different parts added to them later in their lives. The main difference between each controller at the end of the day is material finishings used, simplification of wiring, and ease of use. The only differences between the Block 8 and Block 8A controllers was the use of different lights at the top right, thinning of the metal around the 2 combined switches, and the other testing port to determine the system operability. Later for Block 8As, many got upgraded with different lights for the code operability and system power. These lights could be anything that was on hand at the time. Block 8As in some cases saw changes in the rotary switch handle into the more modern round handle. This was also present from the 8Bs to the 8BKs, even some 8BKs having the older style of rotary switch handle. After the Block AA came the Block 8K controller. The difference between these two was the Block 8K was made of the same material but had a smooth, matte finishing to it compared to the rough finishing the Block 8s and 8As. For differences, the lights for code operability, system power, and interrogated indicator were all mirrored to the other side of the device and changed to more modern lights for the time. The emergency disaster switch also received a color change to red and white to indicate a more serious tone rather than using green. The biggest of all the changes was the change for the rotary switch handle to be made circular. This would continue on to the Block 8B and 8BKs as well. The final change was the radioactive glow-in-the-dark paint was removed from the emergency disaster switch. The Block 8K controllers also made it to where the text was lowered and glass was put over the text to protect the word printing from being rubbed off over time. After the Block 8K came the Block 8K controller. This version of the controller is the most modern version there is. There are not many differences from the 8K and 8AK, but the main differences are the double switch has been deleted and made into one switch, one fuse had been removed, the deletion of the other system operability testing port, and there were red lights installed onto the device itself for nighttime operations. The only differences between the Block 8Bs and 8BKs controllers was the change in the panel design, the change from the original rotary switch to the circular one on the 8BK, and to some extent the 8B, the addition of red lights for nighttime operation on the 8BK as well. To access the internals of the Block 8A controller in later installments is to unscrew 4 screws from the bottom, which will then allow the user to take the back cover off to see the inside of the device. The code selector knob also comes with a cover that requires the top right and bottom left screws to be removed from the dial cover in order to be removed. Although I am not certain if it is present in all Block 8s or even 9s or even 8BKs, within my example at the very least, the device was able to progress to any other code station other than 5 and 6. This can simply be fixed by taking off the main dial cover, which is underneath the code selector rotary switch, which is only held in by 4 screws. After taking it off, which may require a bit of wiggling, we'll expose the dial alongside the tube that contains the spring that is held on by the code selector knob covered in cosmoline or grease, whatever you'd like to call it. Within the hollow space, there will be 12 threaded holes with 2 metal screws sticking out that make it so the device cannot progress past the 2 station numbers. To take these 2 screws out, on the top of the code selector rotary switch handle itself is a screw that, once undone, will allow the ability to take these small screws out. Keep in mind there's a seal on top of this rotary selector switch as well, so to be kept in mind. Or, alternatively, just make the sticking out screws not aligned with the extrusion in the base and put the device back together. This will allow use of all the code stations except for where those 2 screws are. So for me, I can't use stations 5 and 6, but I can use all the other ones.